Welcome back everyone. Welcome to this particular lecture of overview of bipolar junction transistor or BJT. So bipolar junction transistor is a three-terminal device. We can see it has three terminals, emitter, base and collector, where a p-type layer is sandwiched between two n-type layers, or an n-type layer is sandwiched between two p-type layers. So first case we will call it as a NPN transistor, and second case we will call it as a PNP transistors. So there are three terminals in a BJT, both of these NPN and PNP transistor, emitter, base and collector, and there are two junctions. Here is one junction, here is another junction. So this junction is called the emitter base junction and this junction is called the collector base junction. Similarly, for the PNP transistor, this junction is called the emitter base junction and this junction is called the collector base junction. So this is the physical diagram of NPN and PNP transistors, and these are the schematic symbol. So this is my collector, this is my base and this is my emitter. For this NPN transistor, the arrow looks like this. NPN means not pointing in, that is pointing out. So arrow is outwards. But for PNP transistor, pointing in, so arrow is this way. Okay. Now let's move on to how the NPN transistor works. We will discuss in this particular lecture on this mechanism of NPN transistor only. So as we know, this is my emitter, this is my N region, this is my base region, this is my emitter N plus region. We are considering NPN transistor, right? So this is my N region, this is my P region, and again this is my N region. This green color region is N region, this blue color region is my P region, and this green color region is again my N region. Okay, so we have applied for this NPN transistor, we have applied the biasing. Biasing means DC voltage. When we apply DC voltages to different terminals of a BJT, then it is called biasing. So under normal operation, emitter base junction is forward biased and collector base junction is reverse biased. How it is forward biased? You see, N is connected to the negative terminal of the battery. That is why we are calling it emitter base junction is forward biased. And how this collector base junction is reverse biased? N is connected to the positive terminal of the battery. Okay. Now, since this is a PN junction, right? So here, that means in a BJT, two PN junction diodes are connected back to back. Here we have one PN junction, here we have another PN junction. Now, as I told initially that in a NPN transistor, emitter base junction is forward biased and collector base junction is reverse biased under normal operation. And from the PN junction diode mechanism, we have seen that when the PN junction diode works in forward bias, then what happens? The barrier potential between in the depletion region reduces, and it finally reduces the depletion region width. Okay, so this is my depletion region, right, between the emitter and the base. This is my depletion region. So when I am applying this voltage, emitter base voltage, what will happen? This emitter region, it will supply the majority charge carriers, that is electrons, because in N region, what are the majority charge carriers? Electrons. So these electrons are supplied by this emitter terminal. Now, since this emitter base depletion region width is very narrow, or the barrier potential is very low in this region, it becomes very easy. Now we will switch on this diagram B. Now it becomes very easy for these electrons to overcome these depletion region and they reach to the base. And in this base region, all these white colored dots or circles that you are observing, these are my holes, and these black colored dots are, these are my electrons. So when these electrons are coming by to this base region, by overcoming these emitter base depletion region, some of these electrons, they will recombine with the holes, okay, and they will get vanished, okay. But this base region is very lightly doped, and it is very thin. The thickness of this base region is in the order of few micrometer, and it offers very high resistance to the charge carriers. So when these, some of these electrons, they are recombining with the holes, okay. So when these electrons, they are coming to the base region, they have two options. Either they can flow out of the transistor through the base region, or they can diffuse to the collector side, okay. Now as the base region is very thin and very lightly doped, and it offers very high resistance to the charge carriers, so only few electrons, they will be flowing out of the transistor through the base terminal, and majority of these electrons, what they will do, they will diffuse to the N region. Because why? Because my collector base junction is reverse biased, right? So that is why if I increase this VCB, what will happen? This collector base depletion region width will become it will increase, and it will reduce the base width even more and more. So what will happen? In this case, the electrons, most of the electrons, they will reach to the this collector region, and finally there will be collector current will be flowing through the circuit, okay. This is the basic mechanism of the NPN transistor, okay. Now as I told initially that this BJT has three terminals. One is emitter, another one is base, another one is collector. So this emitter region, it is the left side region, left side section. Let's go back to this diagram. It is the left side section of your BJT, okay. And what are the property of this emitter terminal? It is very heavily doped. It has moderate area and thickness, and its main job is to supply the majority charge carriers, okay. If it is an NPN transistor, it will supply electrons. If it is an PNP transistor, it will supply the holes, okay. Now coming to this base region. Base is the middle section of your transistor, so it is very lightly doped and thin, okay. The thickness is in the order of few micrometer, as I already told, and its main job is to provide a path for the majority charge carriers that are coming from this emitter terminal, okay. Now in the collector region, it is moderately doped, but it has largest area and the thickness in the overall transistor configuration, okay. Now BJT can operate in three regions. One is active region, one is cutoff region, another one is the saturation region. We will see how BJT will operate in these three different regions, but let us see what is these operations actually. In active region, this emitter base junction will be forward biased and collector base junction will be reverse biased. In active region, my BJT will work as an amplifier. In the cutoff region, emitter base junction and collector base junction, both junctions will be reverse biased. And here in this cutoff region, my BJT will work as an off switch. And in the saturation region, emitter base junction is forward biased and collector base junction is reverse biased. In this saturation region, my BJT will work as an on switch. Now, BJT can operate in three modes. One is common base mode, another one is common collector mode, and third one is a common emitter mode. So first we will see what is common base configuration. Common base configuration means my base terminal. We have seen that BJT has three terminals, emitter, base and collector. So if it is common base configuration, means base will be common between the input and the output, and this base terminal we should make it grounded. Okay, so rest of the connections will remain as it is. As I told, for normal operation, emitter base junction is forward biased and collector base junction is reverse biased. So when I draw the input and output characteristics for this NPN transistor, how it will look like? If I want to draw the input characteristics means input current versus input voltage for different values of output voltage. So for this common base configuration, this is my input side and this is my output side. So for this common base configuration, what is my input current? IE is my input current. What is my input voltage? VB is my input voltage, right? And what is my output voltage? BCB is my output voltage. So input characteristics we will draw between input current IE versus input voltage VB for different values of BCB. Okay. Now this input current IE is in milliamps. This is important. And as you can observe in this diagram, as we are increasing this collector base output voltage, what is happening? My input current IE is increasing. So what conclusion or what inference we can draw from here? The inference we can draw from here is, see, let's go back to this diagram again. As I am increasing this collector base, BCB is increasing, collector base reverse bias voltage, if I am increasing, what will happen? This depletion region, collector base depletion region width will increase. That means the effective base width will decrease. So the emitter current, what will happen? The electrons that are coming from this emitter region, when it reaches to the base region, it will have a very less chance to flow out of the base terminal. Okay, most of the electrons will reach to the collector terminal and it will ultimately increase your emitter current. That is why we can see, as we keep on increasing the collector base reverse bias voltage, emitter current is increasing. Now output characteristics, how will we draw? Output current versus output voltage for different values of input current. So what is my output current? IC. What is my output voltage? VCB. What is my input current? IE. So that's what we have drawn, IC, which is in milliamps, versus BCB in volts for different values of IE. And this IE is also in milliamps. Now what is the active region? The active region, you can see, as we keep on increasing this VCB, my IC value is also increasing. Collector current is almost equals to the emitter current, as most of the electrons are reaching from the emitter terminal to the collector terminal. So as we keep on increasing VCB, IC will increase. And these are my IC values for IC current values for different values of IE. Okay, so here in this region you can see this current IC, they are linear, almost linear and equally spaced for different values of this IE. As you keep on increasing IE, my IC will also increase. But in this region, IC is linear and equally spaced. So in this region, it is called the active region, and in this region, transistor will work as an amplifier. Okay, that is in the further studies we can see what is. And in the active region, what happens? Emitter based junction is forward biased and collector based junction is reverse biased. Now in cutoff region means transistor is off. Okay, that means both emitter base and collector base junctions are reverse biased. What is this cutoff region? Cutoff region is the region to the right of VCB equals to 0 and below I equals to 0. In this region, transistor acts as an off switch. What is saturation region? The region to the left of this VCB equals to 0. You can see current is exponentially increasing as this VCB, it increases towards this 0 volt. So this region is called the saturation region. Now we will see the same input and output characteristics for common emitter configuration. So common emitter means this emitter terminal will be common between the input and the output, and this emitter terminal will be grounded. So what are the input characteristics? Input characteristics means input current versus input voltage for different values of the output voltage. So what is my input current here? Input current is IB, input voltage is VBE, and what is my output voltage? VCE. If you notice one thing here, input current IB is microampere, but in previous case input current IE was in milliamps. Now we will see why this IB is in microamps. So as we told, same explanation, as the electrons are coming from the emitter region, if we keep on increasing this VCB or collector base reverse bias voltage, this collector base depletion region width will increase and the effective base width will decrease. So most of the electrons are diffusing towards the collector terminal, but only very few electrons, they will have the chance to flow out of the transistor through this base region. That is because base is a thin and the lightly doped region, and it offers large resistance to the charge carriers. Okay, so only very few electrons will get the chance to flow out of the transistor through this base terminal. That is why the base current is very low. As we keep on increasing this VCB and this collector base depletion region with is increasing, the base width will decrease and base current will reduce. Okay, that is why we can observe as we keep on increasing this here. Now my this voltage will be my, instead of VCB, this will be my VCE when we are discussing the common emitter configuration. Okay, so you can see as we keep on increasing this VCE from 1 volt to 20 volt, the base current, it is reducing and it is very less. That is why the value is in microampere. Now output characteristics will be output current versus output voltage for different values of input current. What is my output current? IC. What is my output voltage? VCE. What is my input current? IB. Okay, so you can see this is IC versus VCE graph for different values of IB. Okay, now as we keep on increasing VCE and IB, obviously my IC will increase. But you can see previous case, this IC was completely linear in the active region and it was equal spaced. Okay, but in this region you can see as we keep on increasing this IB, this IC is not equally spaced. Okay, so here also in this region still the graph is linear. This region, that means the region above IB equals to 0 is my active region, and the region below IB equals to 0 is my cutoff region, and you can see at this point my current is going saturated. That means even if you keep on increasing this VCE, the current won't increase further. So this region, that means let's say this voltage, first your IC is exponentially increasing. No, this voltage is Vsat, or saturation voltage of this VC. So the region between VC equals to 0 to VC equals to VCE sat is my saturation region. Okay, as my collector current IC is exponentially increasing in this region. Okay, now but after this point, even if you keep on increasing this VCE, your IC won't increase further because it has already reached to the saturation region. Okay. Now coming to the common collector configuration. In the common collector configuration, here we are discussing all the in configurations for NPN transistor. So in the common collector configuration, the collector terminal is common between the input side and the output side, and collector will be grounded. So what is, if I draw the input and the output characteristics for this common collector configuration, what will happen? I will draw input current versus input voltage for different values of the output voltage. So it will be IB, which is in microamps, and we have already seen the reason why IB is in microamps. So IB versus VBC for different values of this VEC, output voltage. Okay, so here also we can see as we keep on increasing these input voltage VBC, we will get different values of this IB current, and if you keep on increasing this output voltage VEC, you will get this kind of graph. Okay, your IB will keep on increasing. Now if I want to draw the output characteristics, what will happen? Output characteristics means output current versus output voltage for different values of input current. What is my output current? IE, which is in milliamps, and we have already seen the reason why it is in milliamps. What is my output voltage here? It is my VEC. And what is my input current? IB. So you can see as we keep on increasing VEC and IB, your IE is increasing. Okay, and here in the active region we are getting the linear and equispaced graphs of this IE. So this region is my active region. The region below this IB equals to 0 is called the cutoff region, and the region to the left of VEC equals to 0, this region is my saturation region, as the current is exponentially increasing towards VEC equals to 0. And this common collector configuration is used for impedance matching. In this common collector configuration, it offers very high input impedance and very low output impedance.